Hello, this is question number 5.6. In this question, we have to design 3-bit wide positive edge triggered synchronous mod up counter using 3D flip-flops, having active high enable control signal and parallel load facility. So you can see over here that to design this question, uh, we'll be having inputs as enable, the clock, the load, and the what will be the data which will be fixed if load is turned to 1, and the output will be the Q. There will be 3 D flip-flops rather than 4, which is shown over here because we are designing for 3-bit wide. So you can see over here the for every positive clock edge, this D input should go to Q output. So what will be the D input for each stage? So for each stage, if load is set to 0, so the zeroth input of each multiplexer will be chosen over here. So the Q naught with an enable, if enable is 1, uh, will pass over here. So it will be Q naught bar. Then for here it will be Q naught XOR with uh, XOR with Q1, and this will pass. Similarly over here Q naught ANDed with Q1 because here is AND. Q naught ANDed with Q1, then it will pass with XOR with Q2. Now this will become the next Q2. So now let us see the code. You can see over here, as in the circuit, uh, inputs are clock, enable, load. D will be the our data, which will be putting onto our Q. Now Q will be the output. Now you can see over here, temp is a signal which is similar to this Q signal, which is the output. This is initialized to all zeros. Now our process is sensitive to clock. For every rising edge of clock, it will check if load is 1. So if load is 1, it will choose the data. The data should be put onto the RQ, which is our temp, because our temp is directly connected to Q. Now if load is not 1, it will check if enable is 1, then our value should be updated for every rising edge of clock. So now let us see the test bench. So this is the component declaration. Thereafter signal declarations. In signal declaration you can see our data D, which is set to 110, and enable is initially set to 1. Now this is component instantiation. Our clock is toggling at every 10 nanoseconds. Our load, LO, which is our load, which will define whether the data should be put onto the queue or not. So it was initially set to 0. Now after 45 nanosecond, it will go to 1. After 55 nanosecond, it will again go to 0. This we can see over in the simulation also. Our enable will also go off after 200 nanosecond. So after 200 nanosecond, our circuits will stop and the value of Q is fixed. Now let us see the simulation for this question. This is the test bench. Now you can see over here that our Q, which is this, starts from 000, then it goes to 001, then it goes to 010, which is 2 in decimal. Now you can see over here our LO, which is the load, goes to 1 after nanoseconds 45 nanoseconds. Then again it goes to 0 after 55 nanoseconds. So at positive edge of this clock, the data which is 110 goes to the queue. Thereby, after load is 0, so it will up counter from this position 110. So after 110, it goes to 111, then again 00. So rather than going to, after going from 010 to 011, it went to 110 because of LO load. After 200 nanosecond over here, you can see our goes enable goes 0. So after that, our value is fixed to 101. Okay, thank you.